Welcome to this Forum 360 panel, How Propulsion Will Drive Net Zero. My name's Arthur Orton. I work for the Federal Aviation Administration, managing a lot of our aircraft technology research and development focused on sustainability, emissions reduction, noise reduction. Happy to have a pretty diverse panel here from industry and government today to talk about this topic. To kind of set the stage, in recent years we've seen countries around the world, industry groups, NGOs rally around goals for net zero greenhouse gas emissions for aviation, particularly with a 2050 target. This really culminated in 2022 at the International Civil Aviation Organization with a decision to adopt a long-term aspirational goal for CO2 emissions from international aviation, which was net zero by 2050. And amongst these country plans, the US submitted its own state action plan in 2021 and most recently an update in 2024 outlining, again, a consistent goal, net zero by 2050, and areas of action to get there. So those areas of action includes significant contributions in the future simply through fleet renewal, retiring older aircraft and expanding fleets with the latest available technology, but a really important role with advances in airframe and engine technology to drive a new generation of aircraft with greater efficiency and lower emissions. This is also coupled with enhancements to our operational efficiency of our air traffic system and advances in energy sources, sustainable aviation fuels or non-drop-in energy sources. So within this whole context, propulsion plays a significant role in trying to help us reach these goals for net zero, particularly in providing thrust through the most prudent use of whatever energy source is on board. And today we're going to talk about work across the industry, government, and academia, touching on key technologies, how propulsion can help us get to net zero, priorities, and ongoing efforts within the panel members' organizations here. So we're going to start off with some presentations. Each panel member will give a short talk about their perspective, the role of propulsion, and their organization's work. And we'll start things off with Dr. Michael Winter from RTX.
Good morning. On behalf of RTX, Collins Aerospace, Pratt & Whitney, and Raytheon, I'm pleased to be here with you today. Efficiency has always been of critical importance to propulsion systems. 30 to 40% of the cost of running an airline is fuel. In fact, 30 to 40% of the cost of running a modern Air Force is also fuel. So since the dawn of the jet age, engines have been getting better by of order 1% per year forever, all the way back 85 years to Von Ahn and Whittle. A gas turbine engine is the most sophisticated mass-produced device known to humankind, bar none. There's up to 40,000 parts in there. They're spinning at tens of thousands of RPM, and some of the parts are moving within a hair's width of parts that are not. And we develop these across the industry, and we continuously improve these. Now, the efficiency of a propulsion system of a gas turbine comes down to two things: thermal efficiency and propulsive efficiency. Thermal efficiency is what happens in the core. That's the compressor, the combustor, and the turbine, where the air is compressed, the fuel is introduced, and the chemical energy in the fuel is released as essentially motion on a shaft. And propulsive efficiency comes down to the fan or propulsor and the bypass and the nozzle. And the efficiency of the overall propulsion system is really the product of thermal efficiency and propulsive efficiency. At Pratt & Whitney, we introduced in 2016 the geared turbofan. And this was a step change in propulsive efficiency, representing and delivering more than 16% improvement in efficiency. As we look to the future, we see opportunities for even greater efficiency. Number one, going to higher thermal efficiency. Thermal efficiency in engines, again, going back more than 85 years, has improved by about 400%. And if you plot the theoretical stoichiometric limit of where you could get to, we've only come about halfway in all that time in terms of the possibility of ultimate thermodynamic efficiency that could be achieved, accounting for the second law of thermodynamics. So there's a lot of runway. Of course, as you go higher in thermal efficiency, you go to higher pressures, which means higher temperatures, and that means new material systems and better cooling embedded within the hot section of the engine. At Pratt & Whitney, when we introduced the geared turbofan, we also saw that we had to be a bit conservative, and so we only dipped our toe in terms of that new design space. And we see lots of runway going forward to further improve efficiency. So as we look to the future, we will see continuous improvements in thermal and propulsive efficiency. As was mentioned in the introduction, sustainable aviation fuels are here today. There are 9 chemical pathways that are currently approved for use, up to 50% blends. We are also, across the industry, looking to approve 100% SAF. At Pratt & Whitney, all of our modern engines are capable of 100% SAF moving forward through production. And even our legacy engines, including our 5th-gen fighters, can all operate on all of the approved up to 50% blends of SAF today. Hybrid electric. There are wonderful opportunities with hybrid electric. Not so much in going to electrification of flight, full electrification, because batteries represent about 40% more mass on a per energy unit basis than jet fuel. However, hybrid electric, where not in terms of the arbitrage of switching fuel for electrons, but reimagining the propulsion system as a cyber-physical machine that allows you to operate with greater efficiency, we see opportunities across all domains of flight. And we'll talk more about that as we get into the conversation. And hydrogen. We love hydrogen. We've actually developed an engine all the way back in 1958 that ran on hydrogen. It was called Project Suntan. And we see huge opportunities for hydrogen. There are challenges in terms of the oxides of nitrogen, in terms of material compatibilities, in terms of the added water emissions from it. But if you take, and in terms of the storage of the fuel at cryogenic temperatures, but if you combine all that, we've developed a new cycle called the HySite, hydrogen steam injected intercooled turbine engine, that can represent up to 35% more efficient engine, and you remove the carbon atom. And so we'll talk more about those as we get into the panel. Thank you.
Great.
So Steve Wellborn from Rolls-Royce. My current position is Senior Fellow, which is a great title because it means you don't have to moderate what you say as much.
Correct.
So let's start. I could just say ditto, right? We're an OEM, and I could just sit down, but I'll say more. I want to ask a question first. How many people here flew here to this conference? Man, we live a storied life, don't we? It's just great. We get to create the mess and then clean it up afterwards. As an OEM, we have a very similar path as what RTX or Pratt would have. First off, drive continuous improvement to the gas turbine and the power systems, whether that's materials, whether that's cooling, whether it's the cycle efficiencies, propulsive or thermals, right? Going into gearbox, going into component efficiencies, just across the board. We're driving that as normal, perhaps even harder today. Sustainable fuels, right? Everybody's on board for that. Just like our other OEMs, we've proven that we can burn the sustainable fuels. We just had a flight over the pond from London to, I believe it was New York. I don't remember which one. Teamed up with Virgin to do that springtime this year. So very doable. Of course, for me personally, this isn't Rolls-Royce, but that kind of puts the onus on another group of people, the logistics, the supply of the SAF, right? The engineering side of that for for engines is easy, relatively easy. It's all of the support around it, which is much more difficult. And then obviously develop alternatives such as hybridization and hydrogen. We're driving that also. I think more importantly what we see, and I'm sure the other OEMs see, is the enhanced integration at a platform level, whether it's a new concept like RISE, maybe not completely new, but a rehash of old ideas is a great example because you got to get that on an aircraft, right? You actually have to put that engine on an aircraft, whether it's an embedded engine in a military project. That enhanced integration is really, really important to sustain the efficiencies that you're driving for, and at the same time, have it work. We also see manufacturing, digital, and service technologies coming through and how that's all integrated together. I think no longer, and this goes with the other point, no longer are these like wash machines that you just bolt onto an aircraft, right? You have to think of the whole system together. And what I will say also is at the forefront of all of this has to be safety. You can get really excited about all the new technologies, but this stuff has to go on an aircraft and work flawlessly with the reliability that we have today, and it's safe, right? So how many chief engineers do we have in the room? Yeah. Pay a lot of respect to the chief engineers because they have to handle both the safety side and then the overall performance side of these products. And before I get off the stage, I'll make mine quite quick. At Rolls-Royce, we don't only produce gas turbine engines, which is what this panel is mainly about, but we also have other products. Large piston engines that go into marine applications or big construction vehicles. We're on the same path as what a gas turbine would be. And in fact, it might be easier in terms of alternative fuels, as you can imagine. And in addition, we've got a unit off of our subs unit that does nuclear reactors to push SMRs. So as we get into more electrical applications for any kind of propulsion, as the battery weight comes down, you've got to have a power source, a clean green power source to go with that. Now there's other alternatives also, but Rolls-Royce is pushing that also. So I think it's not just the gas turbine portion of this that's important, but how all of that can play together as we go forward.
Great. Thank you, Stephen. And next we have Kathleen Mondino from GE Aerospace.
Great. Thank you for inviting us to be here today. I'm happy to represent GE Aerospace. So I can say ditto to the ditto from Stephen. You're going to find that I think across the OEMs here, there's a very similar strategic path forward that you look at what you can do to the turbomachinery, the alternative fuels, and then bringing in the bigger, broader climate science. It's really more in where you're putting your bets on those technologies. So similarly at GE Aerospace, we're really looking at it in a kind of two-pronged approach that has a lot of sub-pillars below it that I'll talk a little bit about. The first is really focused on innovation for the turbomachinery itself, and then the second is focused on where the compatibility with your clean energy source, whether that is integrating hybrid electric, going further in the future to more electrification, SAF, and possibly in the future hydrogen as well. But going back to the innovations in the turbomachinery is where we're really excited about the open fan technology, and that's what you see an image of here. Back in 2021, we launched the CFM RISE program, which stands for Revolutionary Innovative Sustainability Engines. It's a mouthful. But basically what it means is it's a four-pillar approach, because we like our prongs and pillars. The first one is the open fan itself. So the open fan is all about increasing your propulsive efficiency, like Michael was talking about. You have propulsion and you have thermal efficiency. At some point in time, it gets really expensive to maximize your thermal efficiency. It's hotter, you have to pay for it in cooling, you have to pay for it in material systems. But the propulsive efficiency is really limited by how big you can make your fan and how slow you can move your air across it. So removing that duct unlocks the physical challenge there, and it turns it into an engineering challenge. So with the open fan, it helps unlock that big step change in propulsive efficiency, and that's what we're really excited to be going after. But we don't stop there, because you also need to keep pushing forward with your thermal efficiency technologies as well. So doing that, we also are working really closely with NASA through the high-tech program and also with the FAA through CLEEN, and working on compact core technologies, which are pushing the boundaries there as well. The other pillars are hybrid electric, where we're doing we're working again with the FAA, NASA, through both high-tech and the EPFD program, which Joe's involved in both. And then we're pushing those forward there. They're both focused on learning how to really do that hybrid electric integration and then focusing on how that could be incorporated, like Michael was talking about, in the narrow body market. How can you do this without a battery in a first generation? And then finally, really focused on those alternative fuels. So SAF, right now, just like Michael and Stephen mentioned, all the certified pathways, all of our current fleet can manage those, no problems. And we're working closely with the rest of the industry on what 100% drop-in would be in the future and making certain we are able to accommodate that. And then also the other piece of this is the climate science itself. The more we understand the climate science, the more we can pull that back in and make certain that we have both the engine and the fuel sources that we need to really attack the sustainability problems of today and tomorrow. Thank you.
Great. Thank you. Thank you, Kathleen. And I just pausing there for a moment to reflect, I think we've now heard from our three industry panelists representing sort of the largest propulsion OEMs. And you definitely see some common themes, but you see some differences start to peek out that I'm very interested to get into in the discussion later. So now we'll move over to sort of the government representatives on our panel. And we've got Joe Connolly from NASA.
Well, thank you so much for having me. It's an honor to be on such an established and esteemed panel here. The goal for net zero emissions by 2050 for me is something that's super exciting. We get to be a part of an incredibly hard challenge to see if we might be able to make a huge impact for our climate, our planet, and it's one of those huge challenges that are going to be incredibly difficult to make by 2050, but it's one of those things that we get excited about at NASA to see if we can really make those really hard goals become reality. So following along with a number of the dittos with the other comments here, just wanted to talk about, I'm going to focus more on the electrification side, and we see a number of the transportation sectors moving into electrification. A large part of that for the movement into the electrification area is really the benefit and efficiency with the electric machines compared to other internal combustion engines. So when we talk about the advancement of the electrification in the automobile industry, when we're comparing the electric machines to internal combustion engines, there's a huge advantage that you can get to by moving to electric propulsion. When we start to move over into the aerospace sector, everything gets a little bit harder. My colleagues here with the gas turbine engines and the turbofans, they're incredibly efficient. So the opportunity that we have becomes a little bit more challenging as we start to try to electrify the turbofan engines of the future, but we still find that we have an opportunity there. So as was mentioned, when you're talking about the thermal efficiency and the propulsor efficiency to get over to that overall efficiency of the propulsion system, the current rough estimates for turbofan engines is around the 40% mark, and when we are looking at concept studies at NASA, we are looking for electrification where we might be able to get somewhere in the 75% efficiency. When we found that we have some kind of opportunity there, we started to do trade studies over a decade ago to investigate various concepts of electrified aircraft propulsion. We found plenty of concepts that we tried out that didn't work at all. When you move into the hybrid electric, it becomes really important how you're going to implement the concept of operations and the electrical systems into these future aircraft systems. And we found a number of opportunities that we wanted and pursued, started to do some small hardware studies, and then we started to find some real benefits and make some traction. And then once we got to a higher technology readiness level, then we reached out to our industry colleagues on the panel here and saw what we might be able to do in some partnerships to really demonstrate to see if electrification could be a contributing part of the net zero solution moving forward by 2050. So you can go to the next chart. So I'm working on 2 projects at NASA, both in the hybrid electric area, but I'm going to talk mostly today about the electrified powertrain flight demonstration project. We kicked this off a few years ago. We have 2 industry partners that are working with us, GE Aerospace and magniX. The GE Aerospace, we're looking to basically look to enable a megawatt class powertrain for commercial introduction in the 2030 timeframe. So with GE, we're looking to flight demonstrate the electrical megawatt powertrain on a Saab 340. The parallel hybrid architecture that we're looking at is going to be combining both the turbomachinery of the turboprop and the electrical power system to drive the prop. And on the magniX side, we're looking at, again, doing a regional turboprop demonstrator on a Dash 7, but here we're doing a slightly different parallel hybrid configuration where we have 4 engine aircraft on the Dash 7, so we have 2 fully gas turbine turboprop systems, and then we'll have 2 electric propulsion units that are fully electric driving the outboard engines for the Dash 7. So really excited about being able to not only just look at the propulsion systems where I have most of my focus, but then actually to start to look at how do these systems really integrate in the aircraft system to make this technology a reality and something that we can actually use here by the 2030s and the 2050 timeframe to advance it to a level where we can start to achieve our actual goals. You can go to the next slide. When we first got started at NASA, the introductions for these technologies on the hybrid electric side were identified as a number of key barriers that we thought we needed to overcome to accomplish our objectives. So some of these barriers we've been starting to address ever since we got kicked off on this effort. And a number of the ones that we've addressed in a couple of publications and news articles that have been announced over the last few years is the high voltage at altitude. So we are really excited to work with both of our industry partners here, GE Aerospace and magniX, to do a high voltage electrical powertrain demonstration at our NEAT facility at NASA Glenn, where we're able to basically run the powertrain through a number of different operating conditions and test out the systems on the ground in a simulated altitude environment prior to the introductions of the electrical powertrain on the actual aircraft systems before the flight demos, reducing our risk and ensuring that we may be successful in our future flight demonstrations here in the upcoming years. We've also been working on a number of different challenges, as was mentioned, as we go for electrification. The battery system performance is going to be critical to make sure that we're going to be successful there. So we're starting to look into the introductions of battery testing and how we might be able to incorporate that as well. And as was mentioned, the concepts in terms of how we use the hybrid systems become really important as we're trying to advance the battery technology to reduce that weight for the future systems. At the end of our project here for the EPFD project, our goal is to introduce this technology to a technology readiness level of 6 so that our industry partners can take advantage of that technology and then introduce it into their commercial products for those larger transport aircraft in the 2030s. So thanks so much and looking forward to the panel.
Great. Thank you, Joe. And finally, last but not least, we have Dr. Peter de Bock from ARPA-E.
Thank you. I really actually appreciated all the previous speakers, and I'm here from the Department of Energy. You might ask, what is the Department of Energy doing at an aerospace conference? Well, I represent an agency called ARPA-E, which is the Advanced Research Project Agency for the Department of Energy. So we were shaped similarly to DARPA to figure out what are the transformative, disruptive technologies. If they would work, they would be changing the entire landscape. And one of those take high risk, high reward bets. We actually have to, we get tracked by Congress how many of our projects fail. We have to hit a failure ratio of 50% or more, which is bizarre. But we have to take high risk bets so that we truly push our minds into the next generation of technology. What are the things that can work? If they would work 10 years from now, they would disrupt this industry. So in a way, you can see us as being on the flanks of the industry, trying to see what are the technologies, if they would work, can we have knowledge of those first, so that we make sure that we can incorporate in those technologies. Sometimes I see myself as filling the toolbox for the industry teams, so that they can have access to the best new component technologies first. Now, as an agency, we're pretty serious about transportation. If you look actually at current emissions, transportation sector is actually leading emissions over power generation. And being at the DOE, prior to this I was in industry for 18 years, I saw that the transportation sector will in 2030, 2040 probably get more scrutiny about the efficiency of our work. And Mike very clearly said, and I love jet engines, but 400% improvement is remarkable. And all of you that have worked on that, thank you. But it's still at 40, 42, 40, maybe 45%. Joe showed that as well. So how can we in 2040 say that we have a 45% efficient system and be very, very comfortable about that? And it's difficult. So as DOE, we realized that aerospace is probably the hardest things to decarbonize. So for an agency that's looking for transformative disruptive solutions, it was the perfect space to do some work. And in that we see multiple modalities being the paths of the future. It's an and. Anything you can do fully electric is probably really good. And I'll argue that why. Joe showed you earlier, fully electric, you can push the efficiency into the 80%, 75, 80%. Right? That's from 40 to 80, that's a big deal. The second thing, being at the Department of Energy, I see numbers around the grid. Last year, we curtailed 30 terawatt hours of energy because the grid didn't have room to transport it. In some areas where there's dynamic pricing, there's negative energy pricing. Can you ask your airlines, would you like to get paid to take delivery of an energy carrier or fuel, right? If 30% of your margins, 30% of your budget goes to fuel, would you like to get paid to take an energy carrier? And that energy carrier electricity in some areas is around 2 to 3 cents a kilowatt hour, which is below the chemical value of jet fuel. So I have a cheaper carrier that I can convert at double the efficiency. I think for an airliner that will win. Now the challenge is, right now the capability of an electric airplane is very minimal. Mike will enjoy this, but I looked up Wikipedia and there's a nice chart there that actually shows range versus passenger for many airplanes. And I tried to use that on my chart, but I couldn't, because it started at 1,000 miles and it started at 50 passengers. And I'd have to redo the whole chart because we're at a little pixel on the left right now. And that's reality. But if you look at the technologies that we think are the limits of physics, those pixels can grow. So we launched a number of programs to see what are the limits that could be achieved. There's a number of elements in there. So Ascend is a program to develop advanced drivetrains. We have nine teams in that. It's $63 million to develop the most power-dense drivetrains ever developed. On the right, you actually can see one of the engines. I've shown it to a few of you. This is a Wright Electric 2.5 megawatt electric propulsion engine. They took a Lycoming engine for BA146 and developed an aerospace motor that can operate at 40,000 feet that they stuck in the back of it. They try to fully design a motor for advanced energy density, and that's one of the first one. Currently, it's in Las Vegas at the CES because we like to have a little bit of show power with our machines. But there are other machines coming. Hynetics is here in the room, 40 kilowatts a kilogram. We have many 9 motors, and learn more about that program if you want to learn about aerospace motors. We're very fortunate to have great partners in NASA Glenn, which will test some of our machines in their NEAT facility this year. And we look forward to having series on press releases of having the most power-dense powertrains. And this is not just a motor, it's motor, powertronics, and thermal management all in one. But motors alone don't fly a plane. So Energy Carrier Propel 1K is a program to disrupt the battery space. We looked at the overall battery space in general. We found that the car industry currently is focused on making batteries cheaper. If your car can do 300 miles, most people are satisfied. They don't need a lighter battery. Actually, car companies like the heavy mass because it helps them with the center of gravity. They want them cheaper and at mass volume. So we felt there was a white space in high energy dense batteries, so we decided to fund it. Funded 13 teams, and it's really hard. It's going to take probably 10, 15 years to get these to scale, to explore batteries in the 1,000 watt-hours a kilogram fully packaged. Now, if I combine Ascend and Propel 1K, I'm getting on your chart, Mike, because now I can actually get to 700 miles with 100 people. Or maybe if I put 50 people on there, I can get to 1,000 miles. So I'm getting on the chart. And you might see, I talked to some big companies, and they say, well, that's not even close to what a narrow body can do. And you're correct. However, if you look at the missions we fly, there are a lot of missions that are below 700 miles or 1,000 kilometers. In the US, it's 20%, and in Europe, it's 40%. So will it be 2040? I don't know, but it's our job to try, and maybe we fail. The technologies we have by themselves, better batteries and battery motors, will already find their ways to hybridization of the existing gas turbines. So pushing those technologies has merits for all of those too. In addition, so I see a very narrow pixel zone for electric flight that's going to grow. Then there will be a hybrid zone. This is where we have pressurized hydrogen. We saw a great presentation from ZeroAvia this week, hybrid solutions with SAF. I think the engine is at the emergence of exploring the hybridization as these components get lighter and more powerful. And then beyond that, at some point, maybe full hydrogen. So we're funding all of those. We're funding full hydrogen and high side. We're funding, we also have Green Wells and Reach here. Green Wells is another, I think, a very exciting program. We felt that the grid is currently the bottleneck in deploying more renewables. And there's actually 1.2 terawatts of renewables in the queue. Countries like Germany and France have to, France has to turn down the nuclear power plants when the sun shines because there's just too much energy available. They can't transport it on the grid. So we developed a program where you have stranded or grid disconnected renewables just producing SAF. I calculated how much corn I need for SAF. It's 50 billion bushels of corn. It's kind of a lot of corn. So we felt, can wind turbines by themselves in remote locations start producing SAF, where I don't need to wait for the grid to be connected. So this is another explorative program and reaches how to generate in a hybrid configuration electricity on an aircraft using enhanced APUs. So these are the things we do, and overall the total goal for me is that in 2040 we have a toolbox of technologies that allows us to push the total overall efficiency over the 42% into the 50s, into the 60s, because that's, I think, the kind of technologies we need to develop for the next generation. Thank you.
Okay, great. Thank you, Peter. So now to really start getting into our discussion here, I think you heard pretty much all the panelists and Dr. Winter particularly introducing the concept of sort of, this is a technical conference. We're going to kind of break our discussion into thinking about the propulsive efficiency, the thermal or sort of power generation efficiency, and then a little bit of talk about the energy source. So I guess to start things off, throughout the industry, we're seeing a lot more prominent talk about potential propulsor architecture changes, especially on next generation civil transport aircraft. I guess straight into it, what do you all see as the most likely outcome of open versus ducted versus more creative things like distributed propulsion configurations, and in what time frame, right? We're all working these at different TRL levels. So maybe Kathleen, would you like to start with that?
Well, I think it might be pretty clear where my thoughts on the matter are. Whenever we're looking, and I think you were bringing up the chart with all the range and the seats and the mileage, and we're really laser focused on the narrow body market. It's up for a fleet renewal here potentially towards the end of this decade, the beginning of the next. If you want to start attacking emissions, that's a great place to be ready to go attack it. To do that, you need to make a big step change, and you got to break out of the box that you're currently in. So That's where we have, obviously, the open fan through RISE, and that's what we think the future is going to be. If it was easy, it would already have been done. It does take looking at the engine and the aircraft together as one system that hasn't been done before. Generally, you have your aircraft, and you can put pretty much any engine on it, right? That's the model. There's aircraft, you go to one of us, and you get an engine. That has to change a little bit, and there's no really getting around that. But that's the exciting technologies, and that's the challenge in front of us, and it's what we think is needed to be able to really make that step change, to really have the sustainability impact, and then the value back to the airframers, airlines, and then, flying public as well.
Stephen or Michael, would you like to comment on your perspective?
Real quickly, I think obviously if you're laser focused on one market, there might be one solution, right? I think if you look over the broad area of the difference between ducted and unducted, I think it kind of depends, truthfully. And I hate to say that, but it really does. Maybe for middle of the market or even smaller aircraft, you'd say maybe an open fan or an open rotor type configuration will work. As you go to the larger aircraft, you think, maybe that just stays ducted, right? So I don't think there's a one-size-fits-all right now. Others might disagree.
So at Pratt & Whitney, we love open propulsors. In fact, currently, we make most of the open propulsors that are flying around right now today. They're called propellers. And we understand the technology, and they do have an application, particularly when you're flying a little more slowly, and the safety trades and the installation trades, the penalties in order to protect the fuselage, and the safety trades relative to potential mishaps and intersections of the rotating parts with devices, foreign objects, birds, etc. When you do the full system trade, we are really excited about where we are with the geared turbofan, particularly for single aisle and larger, where greater than 80% of the fuel burn resides today. So for the heart of the market, we see geared turbofans as the future. If there is an airframe demand or a request to go and look at open propulsors, we're ready, we understand it. We also understand what the penalties are to install it safely for the flying public.
Joe or Peter, any comments on propulsor configuration from your perspective?
Maybe just briefly, I would say I don't know if NASA has one direct opinion one way or the other on the ducted or open rotor, but we do try to provide tools and capabilities for optimization and simulation so that you could take a look at the various architectures and do a trade for the concepts and where it makes the most sense, whether it's larger or smaller, as was mentioned on the panel. The other thing that we also try to take a look at is see where there might be a gap in where there's lower technology readiness levels and try to do some more studies and work in that area. So we have a couple of concepts that are looking into that more directly on the distributed propulsion side because we feel like that's a lower technology readiness level. So there's a number of papers that are being presented here on a Susan concept where we're looking at more of a hybrid electric configuration with distributed propulsion to see what advantages could be there, and we might be able to explore with industry partners in the future.
Good, yeah, thank you.
I think Joe's chart showed it really well. It's about efficiency, right? Engine efficiency. I'm purposely saying engine, not thermal efficiency, but engine, let's say the thermal variant of that times the propulsion efficiency, right? Right now, the thermal core is incredible, but you're using advanced alloys that are truly at the limits. So we actually did fund a program I didn't list. It's called Ultimate, where we go beyond nickel alloys into the niobium alloys, 1300C+, ductile alloys, right? So yes, we need to keep the thermal efficiency up, but it gets harder when you get to really high uppers and really high temperatures on the core. So that means the propulsion efficiency will get more attention. Right, the propulsive efficiency, they're a great concept, great turbofan, open rotor. I'd like to see more DEP as well, but I think the bigger challenge is I want to fly more stuff. It takes 15 years to get these narrow bodies out. Let's do something that is, can we fly more things and test more? I worry that the immediate safety certification focus, which is perfect to have, stifles some of our early testing. And I'd like to see more, let's build a plane every year as a country and then figure out what to do, what we learn from it, unmanned. But we have the ability to fly unmanned. Let's do something with that. And I'd like to see propulsion efficiency definitely go into the 90%. It's something that the core will be harder to improve. I do think another factor we don't look at enough is the transients of the entire mission. There are different parts of the mission, and maybe there are some elements of there that we can use, maybe the hybridization, other mechanisms to optimize design. But it's the total. There will be more focus on propulsion efficiency. I think it's an and. I'd love to combine all these technologies together and also add DEP and other concepts and do more test flights. I think all of the room would love that, probably.
Yeah.
So I think I'd like to jump in. I think the one group that we don't have on this stage is the airframer, right? Mm-hmm. And at the end of the day, it's people like Frank Hasselbach or Steve Clark from the majority of the fuel burn, whether that's middle of the market or large engines. Those propulsion VPs or directors at Boeing and Airbus, those guys are the ones that will have to make this real decision working with the OEMs and the government agencies.
And actually that kind of brings me to the next question I wanted to ask, which was about, obviously the propulsion system doesn't exist in isolation. With especially this next generation of engines, whatever that propulsor architecture may be, for whatever size of aircraft class, are there propulsion airframe integration challenges or opportunities that you see in what comes next?
So I'll start. So there are absolutely opportunities, and so there's a couple new airplane concepts that are being developed today. For example, the Jet Zero program, which is funded by the United States Air Force and DIU, which is to the tune of order $250 million. It's a blended wing body, and it basically introduces at the airframe level almost a 50% improvement. We're pleased to be part of that program. We have Pratt & Whitney engines as well as multiple Collins subsystems that are becoming fully integrated onto that aircraft, which is building towards a flight demonstrator. We also see, for example, a NASA partnership with the X-66, which is with the Boeing company and the transonic truss brace wing. And again, it's the integration of the aircraft and the engine. The engine in particular there, if you got these really thin wings, you have to understand that you need to preserve the laminar flow. And so ducted configurations probably will prevail if you need to preserve laminar aspects of the flow at the wing interface. Again, we're partnered with the Boeing company and NASA and providing geared turbofans for that flight demonstrator. And so really it's the interaction with the wing, it's the interaction with the whole aircraft. And then when you look beyond, and we'll talk a little bit, I think, in terms of hybrid or hydrogen, the airframe will play a critical role in the integration of the other systems, right? Because all of the power flows on the airplane, the pneumatics, the hydraulics, the electrical, it's all coming from the engine. It's all coming from that. Even the air you breathe on board is coming from the engine. And so, and when you bear that in mind, you can optimize these things, co-optimize these things in a much more effective way if you're not just looking to hang them under the wing.
Yeah. You go next.
Sure, I can do that. So, I mean, obviously, yes, the integration challenge is there. It's there whether it's a ducted or an open fan, as Michael was talking about. It does present itself with an open fan as well, and it's an exciting problem to look at it as one system together. And it takes into all aspects of it. It's how you install, it's how you integrate with the wing, it's how you safely armor the fuselage, it's how you address noise, both community and cabin noise, all fantastic engineering challenges to go solve. And we're really excited to have some partners in this space. I don't know how many of you were able to join Dr. Messer's talk earlier with Oak Ridge National Laboratories, where he was talking about frontier and supercomputing. So we've been really excited to be able to utilize those compute capacity. And then we've also are really excited about an upcoming, well, just announced grant with NASA and Boeing and GE to look at the integrated propulsion airframe. So we'll be looking at how does an open fan fit in with a wing and looking to unlock new insights that way as well. There's also, we're excited about other programs that we have going on, in particular Airbus installing an open fan on an A380. And it's not obviously the application that a narrow body engine would go on, but it's going to let us really look at how we're integrating that engine and getting that airframer feedback on how we're going about doing that. So we're excited about both of those as well. So it's a lot of challenge, but it's time to move from, again, two things being put together. And as Michael was also mentioning, whenever you get into the electrification and those as well, you have to do it together or you're losing that potential.
So yeah, it seems like regardless of propulsor configuration, we're moving into an era of greater integration at the installation there. I guess, in the interest of time, moving sort of more to the, I guess it will stay in gas turbine frame reference for a moment, the thermal efficiency side and the core. You know, it's not all just what we see on the outside with the propulsor, but there's so much compact, high efficiency core work going on throughout the industry as well. And that really is translatable, I think, across various concepts, right? The turbine cycle is involved in a lot of what we're discussing here, regardless of possible future path. So I guess what are the biggest challenges or opportunities in the thermal efficiency space from your perspective?
I can start. So we've all talked about temperature. Material systems are critical. It's a combination of new material systems like ceramic matrix composites, and across the industry, all of us are actively working on and introducing that material system in appropriate places. Also, in terms of the ability to manufacture really sophisticated inside, the turbine blade is the world's most sophisticated heat exchanger on the inside. And so manufacturing those things, and remember, it's the size of my hand, and it's a single crystal of metal, typically, that's grown around the features that you need to have on the inside. And so the manufacturing technologies are advancing phenomenally to achieve those things. Beyond that, it's the compressor. At the very back of the compressor, as I go to higher pressures and temperatures for more thermal efficiency, the diameter of the compressor gets smaller because I'm squeezing the gas. So the blades at the very back of the compressor are smaller than the nail of my pinky, and they're sitting on a disc, and then it's spinning at tens of thousands of RPM. And so how do you manage that and the leakage around the edge of that? Another sort of constraint, if you think about it, is as the core gets smaller, I've got to get that long shaft through that's going to turn the propulsor in the front. And so the propulsive efficiency is going up, which means I've got bigger diameter propulsors, whether they're open or closed. And so I've got a dinner plate, and it's spinning connected to a soda straw, right? And so the rotor dynamics become another constraint. In fact, we've actually looked at our third generation geared turbofan actually uses the gear system to decouple the direct aspect of that, and so you don't have to live with that constraint. So it opens up new worlds of possibilities as you start to shrink the core.
And with all of that, I almost had the same speech as you can imagine, but with all of that, you still have to ingest the bird, right? And be able to still function, or you have to ingest the sand and make sure it can make it all the way through without eroding the compressor, which would hurt the efficiency also, or end up on the turbine with sea mass, right? And so it's all this environmental activity that you have to also include. So it's not just going to the better thermal efficiencies. You still have to eat all of the stuff coming into the engine, into the core.
Absolutely, and it's not just take a Xerox and shrink it down, right?
Yeah.
All these manufacturing constraints, environmental constraints, so you have to find the technologies that overcome that size as well. So it's an exciting place. That's my background, is compression aerodynamics, and I just love it. It's an exciting challenge to solve, and it's one that has to keep going. You need this compact, power-dense core as Michael was saying, to make certain that you can enable those changes in propulsive efficiency.
And as Kathleen mentioned, there's this bit of a gap right now where we can explore all this stuff before you have to retrofit or put a new engine on a new aircraft. The time frames are looking next decade, right? So we do have the time, I think, to explore all these new technologies.
Great. And I guess thinking about, we've sort of addressed the sort of thermal efficiency or sort of power generation efficiency from the gas turbine perspective. There's sort of the electrified equivalent, whether that's moving into hybridization or full electrification space. I guess starting broadly, where do you, we've seen some research efforts highlighted in your presentations. I guess where do you see the state of maturity? Maybe let's start with hybridization and what you see might be its first applications.
I guess some of the initial applications are probably going to be on a more mild hybrid if we're talking about the larger transport aircraft. But I think the opportunities even for the mild hybrids are pretty exciting for us. Right now, the larger transport class aircraft do have larger electrical systems on them, but they're really just pulling power off of the shaft. And the transition here is really being able to use electric machines to put power on the shafts and take power off of the shafts. That's going to be some of the fundamental changes that we would like to see, even if that hybridization is relatively small at the onset of the introduction of the technology. If we're able to get to that point where we're taking power off and putting power onto the various shafts, that would be a huge step forward where we would be working with the FAA, getting through all the regulations to make sure that we follow the new guidelines that we would have to make those products real. And Kathleen was talking about her passion on the compressor side. My background is on propulsion controls. So all of a sudden, the turbofan engine, we basically had a fuel controller and we put fuel in or put fuel out, and we were pretty much relegated by the inertias of the various shafts. Now that we have electric machines on both of these shafts, we have the opportunity to sort of do different transitions as we go through different flight regimes, like Peter was saying, where we can start to optimize the engine in new ways by putting power strategically on the shafts or off the shafts at different key moments of transitions as we go through the flight regime. So for me, as a controls engineer, I think it's a really exciting time where we get to be more part of the integration challenges and the solutions ahead.
Yeah, and I see the standard center line becoming part of a powertrain system, where we traditionally focus all of our efforts on the extreme details of vent wall contouring, compressor stages, combustor. There will be more of a system approach to how do we move heat around the system, because there is a lot of energy in that engine that's not used for its full purpose. And if you combine that with electrification, what are the transients that you can manage? One electrification startup mentioned that the first time the pilot was doing a test flight, he made a mistake. He did what he would normally do. He said at the start of the runway, and he floored it. And the one engine that was electric responded immediately and almost flipped the plane. And it's like ludicrous mode in a plane, right? So what are the transient things you could do if you have that kind of level of torque available at each instant? So exploring the combinations of that with the gas turbine, the initial stages will be very interesting. What are the things you could do from a controls, flight dynamics? I would love to have a plane that can just fly through turbulence by rapidly changing the RPM, right? Maybe you can do things for that we haven't even imagined yet. Maybe you can do maneuvers that you can't even imagine yet, because now you don't have to wait for those engines to spool up. What are the alternate aspects? I think these are all going to be the next 10, 20 years within our design space, because these machines are getting better. So I think the hybridization part will come. And in addition, on the SAF side, I think we shouldn't forget the NOx emissions as well. I think there's been some great successes in that space. And we did fund also single crystal casting technologies that have been very successful in increasing yield in very short design cycles. So I think there's still a lot of room to be done on the center line, but I do see the center line becoming part of a larger system, where we're looking at all the bleed flows, all the systems around the engine, becoming part of a total drivetrain system. And I think that is more challenging, because we have to think out of our domain. We have to talk to God behold, IEEE people, right? And I try actually in my committee work in IIAA to build bridges between ASME, IEEE, and AIAA, because I think those bridges are the ones that are going to be truly developing the system technologies that are needed.
So we see application of hybrid electric to all domains of flight. At Collins Aerospace, we've developed the motors, the drives, the generators, distribution systems up to TRL6 for about 1 megawatt. And so you can apply that. It's enabling for urban air mobility, and we're demonstrating that today in a Copper Bird equivalent. We call that StepTech, or Scalable Turbo Electric Propulsion. And so we have that fully operational today in our laboratories in East Hartford. We're applying it to a regional turboprop. Regional turboprop, say a Dash 8 100 is 2,000 shaft horsepower, that's 2 megawatts. So you do a 50-50 hybrid, and we're building that. We've run the engine through the full cycle. We've done full throttle already, and we're now integrating that onto an aircraft for a first flight, probably in a little over a year, and but certainly during 2026. And we are actively working on this for single aisle. We have built this already, designed this into an 1100G. That's the engine on an A320. An A320 roaring down the runway, 30,000 pounds of thrust. That's 18 megawatts. So 1 megawatt, same motors, same drive, same distribution systems. Put a motor starter generator on the core, a motor generator on the low spool, and as others said, you can move the power back and forth. We are working with our partners in Europe under clean aviation funding with Airbus, with MTU and GKN to build what's called the switch engine. That is a exact engine from an A320, single aisle engine that will operate and ultimately be proposed for a flight test in Europe using hybrid electric, using these same components.
So I guess thinking at the actual commercial products in the 2030 to 2040 timeframe, where do you all think we might see hybridization or full electric in different size classes of aircraft and propulsion systems? Do we see that in products there? Or is it beyond 2040 for some?
Well, I'll mention what again, back with what we're focused on through the RISE program, it's back in the narrow body market mostly. Although a lot, as mentioned, technology spans several of the other markets as well. We're focused on being able to take the mild hybrid and introduce it in that next narrow body concept like we're talking about. We think that that's a natural entry point for that particular technology. In addition to the EPFD program that Joe walked through and our participation in that program, we also have, in cooperation with NASA through HITECH, the power extraction demonstrator, and which it's kind of similar to what Michael was talking about. You have two different, you have your motor generator on your low pressure spool and on your high pressure spool, and you're getting to unlock all the different modalities that you can then do there, get into some of the controls things like Joe was discussing. And we're really excited about that upcoming testing with that program as well. We think that's a natural feeder right back into learning how to do this in the narrow body space and doing it safely, and really how do you do that full system integration.
And we're going to learn, oh, go ahead.
I was going to say, so at the smaller size, single engine planes, you can already do electric, right? I mean, Rolls-Royce has a speed record for a single engine plane electric. The trick is, obviously, as you go to where net zero really makes, or where you really have to address it, which is middle of the market to the wide bodies. And so I think we would agree with Kathleen, hybridization is the next step. Full electric at that size, I would say no by 2040 or 2050, but that's me.
So as Kathleen said, we're going to learn so much by doing the mild hybrid, because if you look at the certification methodologies today, when you look at the electrical system, it's one set of FAR chapters, and the propulsion system is a different one. We're going to be crossing those over. So we're going to learn so much from this on the hybrid, But there's maybe another angle to this that most people aren't thinking about, and there's two key points here. Number one, if you look at a paper that some colleagues and I published in Nature a little over 2 years ago on the challenges and opportunities of electrified flight, and I suggest you take a look at that, we clearly show that we're a long ways off from having practical economic missions with pressurized cabins for fully electric. However, these mild hybrids, if you do the analysis, you fly a single aisle 10 to 15 times a day, and you do the cycle analysis on the battery chemistries we know today, you're going to have to change those batteries every 2 to 3 years. Now, an airplane that's, let's say, enters service in 2035, for argument's sake, it'll be flying in almost 2065. So you're going to change the batteries every couple of years. You're not going to change those batteries with the batteries that you certified with in 2030 or 2035. You're going to use the best state-of-the-art batteries that fit in the box, don't change the CG of the airplane, and safely can be applied. Number two is electric motors don't lapse with altitude, but gas turbines do, meaning that 18 megawatts sea level static thrust from an engine, when I get to cruise thrust, that's only 7 megawatts. So it may only be 5% on the ground, but that's 16.7% when I get up to the cruise altitude. And so those batteries can be applied for greater and greater mission segments just through software changes through the life of the airplane.
That's very interesting. So we've talked quite a lot about electrification, and we've talked about sort of time frames for degrees of that. We've early on touched on SAF and the drop-in approach. Other non-drop-in energy sources, liquid cryogenic fuels, hydrogen, and all that, where do you all see the state of maturity of that, and where that might, come to fruition, and in what application?
So again, from a gas turbine point of view, I think we've all burned hydrogen and demonstrated that we can do it, even in existing products with a bit of a change to the combustion system, right? So that, again, that's a very doable engineering problem. For me, it's the system integration into the aircraft, right? And you start talking cryogenics and the safety aspects that go with that, you think, oof, right? That's a much more difficult problem than just the engine portion of it.
And beyond that, the infrastructure investment, right?
Yes.
So I mentioned our high-side engine, hydrogen steam injected intercooled turbine engine. This is a program that was funded by Peter and ARPA-E, and we just completed the program. So there's a number of challenges with hydrogen. Number one, the good news is it's 3 times the specific enthalpy. It's 121 megajoules per kilogram, but it takes up 4 times the volume. So to store it, you have to store it as a cryogenic liquid at minus 253 degrees centigrade. Number two, when I burn hydrogen, I make more oxides of nitrogen. That's a challenge. Number three, when I burn hydrogen, I make more water vapor. If you balance the chemical reaction, I went and did this like we all did in high school. I had my daughter check my work. It's 2.6 times more water that you produce. So water is a greenhouse gas, and it participates in the formation of contrails, which also can contribute to global warming under certain sets of conditions. So what we did with HiSight was we took all these challenges, we turned it into opportunity. What we say, thermal efficiency needs cooling. And so we used the cooling to trap the water in the exhaust. We then took that water and injected it as steam in an intercooled cycle. It's essentially a modified Chang cycle from thermodynamicists in the room. And what that does is a couple things. Number one, we demonstrated, and this is one of the first times at this conference that we're sharing this, we demonstrated relative to the certified GTF, 99.3% reduction in the amount of oxides of nitrogen using the equivalent combustor type and cruise conditions. Number two, we showed that we can demonstrate it under the program that we can have a heat exchanger that effectively, without introducing too much pressure drop, captures the appropriate water and survives. And number three, we demonstrated that we captured 1 gallon of water every 3 seconds at cruise conditions, which is actually way more than we needed to complete the HiSight cycle. So really exciting results from that program.
If I can add to that, that was incredible work from your team there, Mike. What we looked at is if you want to fly hydrogen, and they first talked about, hey, something that's 20% more efficient. I told them, I'm not interested, because 20% we're going to achieve with all the other improvements that are going to come. If you really want to make that all the challenges that Steve talked about, you got to put a carrot out there that puts you 40 years ahead of everybody else. So they came back with 35%. Right? And that is, if you could do 35% leap in efficiency, that might be enough big of a carrot to start considering all the other things. And we said, what are the 3 biggest risks that you have? Right? So the water capture, the NOx, other elements. And I funded those. And you know what? They fixed all of them. And I find often we are limiting ourselves too early. I find if you unleash people, and that's what my job is, to unleash them with high-risk, high-reward funding, where I pay 80% of the bill, some really exciting things can be de-risked to a level where, hey, it's a new tool in the toolbox. And the hydrogen flight is extremely hard. I also do fund there's liquid hydrogen storage and there's compressed storage. There's also a third one, cryo-compressed. Vern H2 is a startup in San Francisco. I fund has a new path to storing hydrogen that is denser than actually liquid hydrogen, but you don't have to go to 20 Kelvin. It's 60 Kelvin. It's still cryo. And when they first proposed to me, I said, either you got the best of both worlds or the worst of both worlds. I'm just going to fund you to find out. They've done great. So I think I don't have an alternative right now to do a 16-hour flight. We all love SAF, but do the math. 100 billion gallons of jet fuel in SAF is a lot of carbon you got to find somewhere. And personally, I'm not super excited about using plants to capture carbon and then re-emitting it and claiming it's good by a bookkeeper. I like to just do complete zero, so I don't have an alternative for complete zero for wide body long range. Therefore, I have to explore hydrogen as much as I see the challenges. But I'd love to find people to find alternatives. Now, people have approached me with fusion jet engines and other things. Those are maybe a little bit too far out. But let's explore hydrogen with an open mind, because I've seen that if teams get really creative, they can do incredible things. And I want to commend this team on their work. It was Neil's Hill as well, and it was really interesting to see what you could do, unleashing some bright minds at a company.
I think, looking at the clock here, we're going to move to audience questions shortly, but I think that sort of brings us back to this theme that we're working many different potential solutions for different applications and in different time frames. And I think while there is competition, of course, in the industry side, there's certainly a lot of collaboration we've heard referenced on the stage here today, especially between government agencies, with government and the industry, with academia as well. I guess what more can we do? How can we improve and evolve? Because this net zero goal is very hard.
So I'll maybe start, and it's the government, industry, and university partnerships. We have a huge opportunity right now in terms of STEM, science, technology, engineering, and math, and to inspire the next generation. I mean, if you look at, for the last 15, 20 years, we lost a lot of really good talent to tech. And right now, if you look at aerospace, right, we've got the new space economy, we have defending our freedoms, and we have sustainable aviation. Aerospace is cool again. And so let's harness that, particularly in the universities. And I know there are a lot of students at this conference. 2,000 students registered for this conference. I'm speaking to them. This is a really unique time and a great opportunity.
Yeah, I'd double that comment. It is a very exciting time. I remember coming up through grad school, the thought was gas turbines was a sunset technology, and it's just not a sunset technology. It's going to be there. Whether it morphs into hybrid, whether it morphs into electrical, you still need a propulsor out there driving the flow, right? So yeah, I agree. Very exciting time.
So kind of echoing the sentiments so far, but I think one thing that's really exciting is that it's right now. It's not 15 years in the future, it's not 20 years in the future. To make certain these technologies are available in those timeframes, you're doing the work right now. So one stat that near and dear to my heart as a technology maturation leader for RISE is, as the CFM program, were over 250 tests in just a 3-year time frame. I've never seen testing like that go on that quickly on one program, and it's a great time to go and not just learn, but get in there with the tests, really understand the physics of what's going on.
Get your hands dirty.
Learn, and then put it back into what you're doing to continue. So it's an exciting time. A lot of that testing is being done, like we've been talking about, with government, academic, and other industry partnerships. And we just need more. We need more of all of it. We need more people who are interested in getting into it. We need to do more testing. We need more lower level TRL, technologist ready level. We need higher TRL, like Peter was saying, let's do a flight test a year. Like, you know, those are...
But also then the combination of not just tests, but simulation and testing.
All of it, yep. Kind of going back to what Dr. Messer was talking about this morning, we need to make certain that we're also doing the analysis and being able to build those compute capabilities to get new insights, and it all infuses back together, and it's just a really exciting time to be in the industry.
I definitely think that we have a huge opportunity with the net zero. With NASA, we have a mission to inspire the next generation of students and engineers to come into this field. One of the things that we've done is to have a sustainability ambassador group. So we have a whole cohort of interns that come in over the summer that work together in a more collaborative space, get to meet with a number of the NASA leadership team working in sustainable aviation. And then just sort of piggybacking on a number of comments in terms of this area has been a boon in a lot of testing and new labs coming on board. We didn't really have the ability to test a lot of these hybrid electric systems in a number of our traditional facilities, so we've brought a number of new ones on board. So one of the great advantages that we've had recently is being able to bring not just the cohort, but then directly put them in the lab so they get hands-on experience, not just coding and simulation type experience. So it's been a lot of exciting times. And then working with Peter in terms of seeing when we can introduce that advanced technology for the kilowatt hour battery and put it into the systems, into that volume, like Winter was saying, in terms of having that advantage, so that we can make progress over time in a more readily fashion and adopt the technology.
I'll be very brief, but aerospace is exciting. It excites me. When I speak in other conferences, I speak a lot of the data center world and other areas as well, I tell them, you probably flew on a plane. You were going above the clouds, 500 miles per hour, you're probably drinking a coffee. That's incredible. That is a human pinnacle of achievement, and it just marvels me every time. And we do it with 9/9 of reliability. And other industry sectors don't do that. So the skills you learn in aerospace are bar none. And bringing that perspective, and as the world is changing, it's an extremely exciting field to be in.
Great, thank you very much. Moving to some of the questions we've seen online, I think we have time for one or two of these. Sort of a theme here around certification challenges, and a couple questions specifically around open rotor approaches. Not only just, maybe we'll start there, not only just certification, but also sort of public perception on system safety and things for that. Maybe Kathleen, if you could start with that.
So safety is our top priority. I mean, it's a simple statement, but it means an awful lot. There's a responsibility to be safe in this industry, as we've talked about a lot. Pretty much everybody here got on a plane to get here. There's a lot of responsibility that comes with that, so we're very focused on safety as the first priority. Whenever it comes to regulation, we're engaged with all our regulators, with FAA, with EASA, and we're working through those challenges and what that might look like and be in the future. I think a lot of the new technologies that we've talked about today all have some piece of that regulatory challenge with it, so it's an ongoing and in dialogue that's happening as we speak.
Yeah, and in some cases you're helping to develop the regulations with the governmental bodies. That's open rotor 15 years ago, when we had a nice program with Airbus on that, we found that we had to work with the EASA to determine what those regulations would be going forward.
And I guess speaking from my experience, leading some of these research programs for FAA, on the other side of the FAA, the aircraft certification side of the house, we're trying to bring in some of those experts earlier in the R&D process to see what's coming, raise the concerns, and make sure that we're addressing all of that.
Yeah, they influence both. It's an ongoing conversation.
And any new technology that gets introduced must be as safe or safer than anything that's been flying previously, and that informs our decisions every day.
Absolutely.
I think we'll go with one last question because it's the highest remaining upvoted one. We talked about hydrogen as a non-drop-in fuel, but we talked about some of the infrastructure and supply chain challenges. Is there consideration for something like liquid natural gas instead, or other non-drop-in fuels?
So I'll start. If you look at some of the studies out of the Princeton University energy labs, the natural gas infrastructure in the United States today leaks about 2.5% to 3%. And so if you look at the ratio of the global warming potential of CO2 versus natural gas, depending on how long you integrate for, it's somewhere between 28 and 50 times worse. And so if you do the math on that, it sort of guides you to probably it's not such a great idea. There are also enthalpy considerations there. I will say though, with high-site, an engine, if you're starting that's 35% more efficient, then you could buy a lot of infrastructure by introducing, if you're taking advantage of the fact that you have the cryogenic on board, now you can take advantage of that in terms of the engine efficiency cycle. Now that's going to buy and it's going to pay for a lot of that infrastructure.
And in the REACH program, we opened the fuels to anything that people wanted to propose. And we have LNG, ammonia, hydrogen. And I think I would prefer something in the liquid space on ethanol or DME. But personally, I think it's hard. I like to go to zero rather than net zero because that's just my personal projection.
And I think to wrap things up, I think I'll ask one last question here from the audience. We talked about, as Steve mentioned, to take advantage of hybrid, we need to sort of do a combined airframe propulsion system development together. I think we talked about some of that in the PAI discussion earlier. Historically, the propulsion system and the airframe have sort of been developed a little bit more separately, but how do we bridge this divide and try to make sure that we get really the best solution for the next generation propulsion system, not just on its own?
Yeah. You have to start early, right? It can't just be bolted on, and you have to start in those early discussions of both the new concepts and existing concepts and come together from a prelim design point of view is what I would say. You can't just do it after the fact.
And the unlock comes from the model-based digital thread. Yeah. As you say, take your requirements from a stack of papers to essentially a set of models that can now be iterated between the airframe company and the engine company. This is what's happening in the military space today, and it's been hugely effective where we do a high degree of integration as we introduce the model-based digital thread across the entire life cycle. It's an unlock to be able to do that.
And maybe I just mention one other item. So it's early, it's the integration, and it's also a great place where our government and academic partners can play a huge role. It's a dynamic in the industry that's going to have to change over time, and it's a great place for a lot of the work that's being partnered with our government partners to step in and help push some of that forward, especially early. So.
Yeah, and maybe just a comment on what Peter's saying, trying to do that flight demo more regularly. When we got the opportunity due to the Electrified Powertrain Flight Demonstration Project, those opportunities don't come around all that often. So we really wanted to take advantage of the ability for our partners that we selected to also work with airframe manufacturers or integration pieces. So encouraging that piece of it with GE partnering with Boeing and magniX partnering with Aerotech. Hopefully those discussions and how that's being incorporated on the flight demos can then translate to future learnings for the actual commercial products.
Great. Well, thank you very much. I think we're just beyond time. I really enjoyed the discussion. I wanted to thank the whole panel here. Thank you all for your participation and good questions online. So thank you very much.